For this week, we'll start diving into natural language processing, or NLP for short. So, the fundamental problem we have to solve for this field is that computers don't understand text the way we do. Sure, they can display text and store it using Unicode, but that method doesn't give insights to the meaning of the text. So the question is, how do we create meaningful numerical representations of text that computers can understand and work with? We'll start by looking at the rule-based approaches into giving an answer to this question. These were largely used before the mainstream NLP research direction turned towards AI and neural networks when they came along. Do be mindful that these representations were usually tailored to specific tasks respectively, as there was no generalized way to represent language that worked well across different applications before. While these older approaches are less relevant today, they represent crucial milestones in the evolution of NLP, helping to shape the advanced techniques we now rely on to generalize language processing more effectively. So let's start with something called tokenization. Imagine teaching a child to read. You wouldn't start with complex paragraphs. Instead, you'd begin with individual letters, then move on to syllables, and finally whole words. Tokenization works in somewhat a similar way. We break down large stretches of text into smaller pieces known as tokens. The primary purpose of tokenization at this stage is to simplify text to the point where we can systematically apply rules to convert it into numerical representations. So, how should we break a sentence down into simpler fragments? A simple idea could occur in your mind, like, just separate the sentences by periods, or just separate the words by spaces. Well, language is a lot more messier than you think. Just take a look at this example. We're moving to the LA. My goodness, there's a mountain load of grammar flying around here. Abbreviations, contractions, quotes. If we just take a space separation approach, we'll quickly find out we get tokens like LA or we are, which have our words matched up with punctuation marks. At the tokenization stage, our goal is to reduce complexity and standardize the text, so that's not something we'd like. Because these tokens would be treated as distinct entities even though they represent the same words as LA without the punctuation. The computer doesn't see them as the same thing. That's not even considering the noisy text data that could be on the internet, where humans aren't even speaking human language properly. Well, after we've split the text into these basic tokens, we can do a few techniques to further simplify and unify the tokens, like removing stop words, removing punctuations, stemming, and lemmatizing. Stop words are common words like z, is, and, but, and on. These words occur frequently in text, but typically carry little meaning or significance for most NLP tasks, so we just delete it. As for removing punctuation, you already see why, right? Punctuation can create inconsistencies in tokens, such as hello, hello, or hello, being treated as different tokens when they essentially mean the same thing, so we just delete it. Stemming is the process of reducing a word to its stem or root form, typically by stripping suffixes. For example, develop, developed, developing, development, all stems to develop. And lemmatizing, on the other hand, is reducing similar words to one word called the lemma. For example, drive, drives, drove, and driven all turns into drive. The difference between stemming and lemmatizing is that stemming to a stem might not always give a valid word in the English dictionary. Lemmatizing, it does. This is what we call the pre-processing of language. These techniques aren't used today, and we can already start to tell why, because we lose too much context and information of the words being used in the text. Now that we broke down text into these individual pieces of words/tokens, how do we turn them into numbers? We will only discuss some systematical methods used for different goals. Let's look at our first model, label encoding. This is as simple as it gets. We have a list of words, each assigned with a numerical value, and call it a vocabulary. Then for each token in the text, we try to match it with a word in the vocabulary and let it be represented by the word's numerical value. For example, our vocabulary can look something like this: apple being 1, banana being 2, and cat being 3. Then, for instance, if we have the sentence apple, cat, banana, banana, using our example vocabulary, for every token in our text, we look it up in the vocabulary and replace it with its assigned number. In this case, it will be replaced as 1, 3, 2, 2. But is this really meaningful in its representation? Like, does this mean banana is somehow greater than or closer to apple than cat just because they're values? No, it's all just thanks to alphabetical order. Also, if we had a larger vocabulary, this message starts to explode in numerical size. Just imagine all the words in the Oxford Dictionary, or something like that. Also, it's possible we encounter tokens not inside of our vocabulary. Then an unknown token has to be put in its place. This method doesn't have a specific application, but rather it's the literal most basic way to turn words into numbers. Another method that is used is called bag of words. Basically, when given a piece of text, after we tokenize it, we tally the count of individual tokens up and then use that count as the vector representation of the text. For example, given the sentence, the cat sat on the mat, the cat is happy, the tokens might look something like this. A vocabulary of unique tokens is created from the text in the order that they first appeared. For this example, they would look something like this. Then we count how often each word appears in the text. For this example, the appeared 3 times, cat appeared 2 times, sat on, mat, is, happy, all once. The text is represented as a vector of word counts corresponding to the vocabulary. 3, 2, 1, 1, 1, 1, 1. Each position corresponds to a word in the vocabulary. And it can be used in simple tasks like binary classification. In the case of spam detection, if you wanted to classify emails as spam or not spam, you could tally the occurrences of words like money or free to help make a decision depending on if they meet a certain threshold or not to be a spam email. But again, bag of words don't consider context. So a sentence like, me eat ice cream, would give the exact same result as ice cream eat me. Assuming we have a predefined vocabulary of something like this, the bag of words representation for both sentences will look identical. 1, 1, 1, 1. Also, it's inconsistent in creating word vector representations of text in unified lengths, as different texts would have different lengths vector representations, not something good for our machine learning models. The last method that we will take a peek at is hidden Markov models. A Markov model is a statistical model that represents a system that transitions between a finite set of states, where the probability of transitioning to the next state depends only on the current state. In hidden Markov models, the states of the system are hidden and cannot be directly observed. Instead, we observe outputs, or emissions, that are probabilistically related to these hidden states. I'm not going to explain the details of a Markov chain here, but the big idea is that you can sync the words of a sentence transitions from other states based on previous states, like a noun transitions to a verb or a verb transitioning to an adjective. Similarly, for each word, we have a probability of its appearance given a hidden state. Then with a sentence, like, the cat is fluffy to the, and we need to predict what comes next, we can use these probabilities to infer what's likely to come. Since the is a determiner, it's likely to be followed by a noun, and from the list of nouns, we pick the one that is most probable in this context, touch. But hidden Markov models still have their own problems. They assume that the current state depends only on the previous state and that observations are independent given the state. But in language, are the upcoming words independent of the previous context? Well, no. Let me give you an example. I'm going to the bathroom, I'm going to take a. Clearly, whatever you saw as the last word there took the context of going to the bathroom. But hidden Markov models can't model this context. Now, feel free to dive into information theory and so on for details of Markov models. Information theory even comes back later on in a lot of domains in AI. Now that we've seen some of the ideas sparked behind humans trying to manually tune numbers, vectors, probabilities, whatever they got to turn words into meaningful numerical representations for machines to understand. I'll then raise a question. What if we don't have to manually create representations of text ourselves, but instead somehow let a neural network learn and create it themselves? This is the idea behind Word2Vec. Instead of hard-coding rules or counting words, Word2Vec uses a neural network to learn from text data, creating representations of words that are both compact and effective for NLP tasks. But that still gives us a problem. If you've ever seen of this meme, we're sort of at this stage. I need you to help me numerically represent words. I need word representations first to input to the network. But I'm here to get word representations, not give you them. But I need word representations to input to the model. How am I supposed to get word representations if I don't have them? Word representations! Just kidding, we aren't in this endless cycle. The researchers that came up with the Word2Vec paper made a really clever decision. The vector representation of words, word embeddings, aren't the inputs or outputs of a neural network, but rather from the intermediate part of the neural network inside the weight matrices. They are the byproduct of training two neural networks, SIBO and skipgram. So how do we let these words be represented by vectors to input into a neural network? We'll use something called one-hot encoding. One-hot encoding is a method for representing categorical data as vectors, and we can think words as individual categories. So say we had this vocabulary of cat, dog, fish. Then we'll assign each word an index, a unique position in this list, like label encoding. Cat represents index 0, dog represents index 1, fish represents index 2. For each word, its vector representation for inputting to a neural network is a vector where a 1 is placed at the index corresponding to the word, and all other positions are 0. Basically, we have a 1 indicating the presence of that category, and 0 indicating its absence. But since it's one-hot encoding, only one of those indexes will be 1 and the rest will be 0. For example, cat will be 1, 0, 0, dog would be 0, 1, 0, and fish would be 0, 0, 1. This is great to input into neural network models, as all vector representations have the exact same dimension. The length of it is the number of individual words/tokens we have in our vocabulary. So it's very similar to label encoding, except we don't use one number, which is the order it is in the vocabulary for representing the word. We use a vector, and its index in the vector that is 1 for representing the word, and that index number is the same number as the order it is in the vocabulary. Now that we understand how a word is being represented at the input, let's understand what those models are doing and how to use the intermediate hidden layer of the neural network to model language. So let's look at SIBO first. In SIBO, the model aims to predict the target word based on its surrounding words, basically a certain number of words that come after it and before it, which we call context words. The word that we are predicting is called the central word. Let's say the current sentence we're looking at is, I saw a cute cat playing in the garden, and we are at the beginning of the sentence. So, I saw cute cat is the input features, and our label to predict is all of them as one-hot encoding vectors. Let's make an extremely simple SIBO network with the lengths of 2 context words, meaning that we can see 2 previous and 2 after words of our prediction word as the input. And in our vocabulary, we will have a total of v words, and we wish to have word vectors of n dimensions as the representation. Then for our neural network, we would have 4 distinct inputs, all as 1 times v input dimension vectors. They multiply by the same w1, which is a v times n size weight matrix, and then sum together as a vector of this hidden layer, which is of size 1 times n. Then this vector multiplies by w2, a n times v size weight matrix, to map out our output vector of size 1 times v. This output vector is intended to act like a one-hot vector to predict what central word should exist between the context words, but unavoidably it is not. It will converge to a one-hot vector as we train. Another way of thinking one-hot vector encoding is it being a probability distribution where all other probabilities are 0, and the probability of the ice index, whichever that index represents, as 1. By default, the output of this neural network is nothing of a probability distribution. The sum of all the indexes add over 1. So we let it go through the softmax function, such that the addition of all elements in this vector will add up to 1, making it a probability distribution. Then, using the example we had earlier, we multiply each one hot encoding vector of I, saw, Q, gray to W1 respectively and sum them. Then from this hidden vector, we multiply W2, get an output which we put through the softmax function, and then use the cross-entropy loss, a loss function specially used for probability distributions to backpropagate and update weights. I'm not going to go inside the details of the matrix multiplication, but in the end, each column in the matrix W1 contains the context vector for the words, while each row in the matrix W2 contains the central vector for the words. The central word vectors are what we want in the end. Why? Well, to simply put it for the context vector matrix, if you multiply a matrix with a one-hot vector where, say, the second index is 1, only the second column's value will be returned from the matrix. Hence, it becomes the context vector representation for that word which has this one-hot vector representation. For the central vector matrix, if we want the softmax output of the multiplication of a vector to a matrix via one-hot vector where, say, the second index is 1, only when the multiplication of the second row and this vector results in a significantly larger value than the multiplication of every other row in this vector, the softmax output will converge to its one-hot vector representation. And this is the central vector row that will correspond to this word with this one-hot vector. As for training this network, we basically just keep iterating over our text data, updating our context vectors and central vectors. So like, we were originally using I, saw, Q, gray as inputs, and desired output is then we move on to saw a gray cat as inputs, and desired output is Q, and so on. The other idea of skipgram we'll just shortly cover. It's basically the reverse of SIBO. The model aims to predict the surrounding words, the context words, based on the central word. I mean, from the brain of a human, this sounds a lot harder, because we're guessing surrounding words rather than filling in the blank. Then our network will be literally flipped around, so to call it. We can still use this example, and now the inputs would be and the outputs we're trying to predict would be I saw Q cat. Oh yeah, now each column in the matrix W1 contains the central vector for the words, while each row in the matrix W2 contains the context vector for the words. So, how and why are these numerical vector representations of words meaningful, so to call it? Well, think it this way. Individual elements that make up a word vector represents different aspects/dimensions of each word. Like, we wouldn't associate cat as something with royalty, so they have negative values, indicating maybe an antonym, like betrayal. But we certainly do for kings and queens, so they have positive values. And words like man aren't really for or against the aspect royalty. And if we think about it this way, where individual elements make up the different aspects of a word, then similar meaning words should be close together in the higher dimensional vector space. This is a 3D representation of word2vec 10K vectors. And when we search for the word comedy, we'll find that it has words close by in vector space, like drama, television, films, TV, episodes, all words relevant to the idea of comedy as we see on TV today. There are more advanced methods that consider the context which the words are in and adapt the word vectors inputted accordingly, like glove and Elmo. That's a whole other story of how large language models things got names from Sesame Street. Like, look at these two sentences. Her voice had perfect pitch, and he threw the ball with a fast pitch. Clearly very different context, but in our word2vec case, it treats the word vector for pitch all the same, using the same word vector, which might not be ideal for all contexts. Now, with these word vectors, what are we going to do with them? Obviously, check them into neural networks to perform some tasks, but we're going to introduce new architectures in neural networks for dealing with specific tasks of natural language processing. And so, next lesson our goal is to understand about recurrent neural networks, long short-term memory neural networks, seek-to-seek, and the basis of attention. I promise you the ideas link one to another, and it should feel rather intuitive as to how we get there.